Everyone in AI right now is, completely obsessed with compute. We talk about FLOPs, clock speeds, how many GPUs are in a cluster.
Hmm.
But if you actually dig into the performance logs of a big model, you see something totally different. The chips aren't really struggling with the math.
No, they're struggling to stay fed. It's the classic memory wall. The processors are just so fast now, they can crunch numbers so efficiently
Mhm.
that they just end up idling,
Right, just way
just
out.
waiting for data to get to them. It's like a tiny microscopic supply chain crisis.
And that is exactly our mission for this deep dive. We're going to look at how we break through that wall. We're tracing the evolution from the original flash attention paper by Tri-Dow
Which really changed the whole game.
all the way to a very dense, super technical lecture by Jay Shah on Flash Attention 3.
And this isn't just a simple software update. This is a complete re-engineering of how the algorithm talks to the hardware.
Yeah.
We're going to see how moving from an NVIDIA A100 to the H100 GPU actually broke the old optimizations. And fixing it meant going all the way down to managing individual threads and groups of threads.
Okay, so let's start there with that fundamental bottleneck. The core of any transformer, what powers GPT, Claude, all of them, is the attention mechanism.
Right, and the math there means you're comparing every single token to every other token in the sequence.
So it's quadratic, it's n squared.
Exactly. As your context window gets bigger, say you feed it a whole book instead of just a paragraph, the cost doesn't double, it quadruples. Triple the text, it's 9 times the work.
But the original Flash Attention paper, their big insight was realizing the bottleneck wasn't the FLLPs, it wasn't the math.
No, it was the I/O, the input-output.
Okay, let's break that down.
To get this, you have to picture the memory on a GPU. You've got HBM, high bandwidth memory. That's your, say, 80 gigabytes of VRAM.
Yeah.
It's huge, but it's also relatively slow.
So let's use an analogy. The HBM is like a massive warehouse down the street. It holds everything, but it takes time to send a truck over.
Perfect. And then, right next to the compute units, you have SRAM, shared memory. It is orders of magnitude faster than HBM, but it's tiny.
How tiny?
We're talking about 192 kilobytes.
Okay, so a giant warehouse and then a tiny little countertop where the actual work happens.
Exactly. And the problem with standard attention was the traffic between them. It would calculate this massive intermediate attention matrix.
The big N by N one?
Right. Which doesn't fit on the countertop. So it calculates a piece, writes the whole thing out to the warehouse, and then immediately has to read it back in to do the next step.
You're just bottlenecked by trucks driving back and forth.
That's the I/O bottleneck. The chip is just waiting. Flash Attention 1 solved this with 2 main ideas: tiling and recomputation.
Tiling makes sense. You just break the problem into smaller blocks that actually fit on the SRAM.
You got it.
Mm.
You load a small block of your Q, K, and V, you compute the attention for just that block, and you finalize the output right there on the counter. You never, ever write that giant intermediate matrix to the warehouse.
Which must save a ton of bandwidth. But recomputation, that's the one that sounds counterintuitive, doing the math twice to go faster.
It does sound backward. When you're training in the backward pass, you need those intermediate values you just threw away. The old way was to save them.
In the slow warehouse.
Yep. Flash Attention just says, nope, don't save them. Just calculate them again.
Because the math is so much faster than the memory access, it's actually cheaper to just redo the calculation than to go fetch the saved result.
Exactly. Completely flips the logic of the memory wall on its head. You do more FLOPs, more math, and you get a 3x speed up. And crucially, your memory scales linearly, not quadratically. That's what unlocked the giant context windows we have today.
So Flash Attention becomes the industry standard. It's everywhere. But then hardware moves on. NVIDIA drops the H100, the Hopper chip.
And according to Jay Shah's lecture, this created a crisis. It's a classic problem. Flash Attention 2 was perfectly optimized for the last generation, the A100. When they ran that same code on this new, super expensive H100, they were only seeing about 35% to 40% utilization.
That is shockingly low. You buy the most expensive chip on Earth, and it's just sitting there doing nothing 60% of the time.
It really shows that theoretical peaks mean nothing if your software can't speak the chip's language.
Yeah.
The H100 had all these new asynchrony features. The old code was just ignoring.
Like having a second engine you never even turn on.
Pretty much.
Yeah.
But we're talking about WGMMA and TMA. Those are the keys to Flash Attention 3.
Okay, let's break those down. WGMMA.
That's Warp Group Matrix Multiply Accumulate. Basically a huge specialized instruction for doing matrix math very, very fast. But the real game changer here is the TMA.
The Tensor Memory Accelerator. The name sort of gives it away. It moves the data.
It does. But in the past, the threads, the little workers doing the math, also had to go get their own data. They'd have to stop calculating and say, okay, time to go get the next tile.
A context switch. Like a chef having to stop chopping to run to the fridge.
Perfect analogy. The TMA is a dedicated hardware unit that does that for you. You just give it a command, fetch this data, and it does it in the background while the math is still happening.
True asynchrony, but you have to rewrite your whole algorithm to use it.
A complete rewrite. And this is where Shah's lecture gets into the producer-consumer model. It's about restructuring the entire workforce on the GPU.
Yep.
They use what's called warp specialization. A warp is a group of 32 threads. Instead of having every warp do a little bit of everything, they give them specialized jobs.
You have producer warps and consumer warps.
And the producer warp is fascinating. Jay calls it a dummy warp. Its only job is to talk to the TMA. It says, go get the next block of data, and then it's done. It just manages the logistics.
So it's like the expediter in a restaurant kitchen. It doesn't cook. It just makes sure the ingredients get to the line chefs at the exact right moment.
Exactly. And the consumer warps, they're the cooks. They don't have to worry about fetching data anymore. It just appears for them in shared memory. So they can spend all their time just crunching numbers with the WGMMA units.
And you've explicitly defined who does what, so the compiler doesn't have to guess.
And that lets you do what Shah calls ping-pong scheduling. You have two groups of consumer warps, while Group A is doing the heavy matrix multiply.
Group B is doing something else.
Right. Group B is doing the softmax calculation, which uses a different part of the chip's math unit. Then they use these barriers to sync up and swap jobs.
Ping-ponging back and forth. So no part of the silicon is ever idle.
It's a perfectly choreographed ballet of data.
Okay, we have to go a little deeper here. Because it wasn't just about moving data. They also wanted to use lower precision numbers, FP8, to double the throughput.
Right.
But that created this, what you called a Tetris problem.
This is one of the thorniest parts of the whole thing. That WGMMA instruction, the super fast math unit, is very, very picky about the shape of the data it receives. It has to be laid out in memory in a very specific way.
Okay, so without getting too deep into linear algebra, the value matrix just shows up in the wrong shape.
It's a square peg for a rectangular hole. You have to transpose it, flip it on its side.
And you can't just write it back to memory and read it again, because that's the whole memory wall problem we're trying to avoid.
We can't go back to global memory.
Yeah.
So they implemented an in-kernel transpose. Remember our producer warp, the expediter.
The one using the TMA to move data.
It gets a second job. As the data arrives in the fast SRAM, that warp uses the registers, which are even faster than SRAM, to reshuffle the data right there on the fly.
So the expediter is basically chopping the vegetables while carrying them over to the station.
It's an incredible piece of micro-optimization. Jay Shah talks about using specific instructions to just swirl the data through the registers so by the time the consumer warp gets it, it's perfectly aligned.
You know, that specific detail stood out to me because Shah made a point about AI code generation. He basically said an LLM couldn't write this. Not yet.
That was a striking comment. He said that automated tools, even something like Torch.compile, they just can't figure this out. It requires a physical intuition for how the bits live on the chip. He said it was trial and error.
It's more physics than it is logic. You have to know the actual topology of the silicon.
You're basically playing 4D Tetris with invisible blocks of data without stalling the pipeline for a single nanosecond.
Speaking of the human side of this, there is this really charming detail about Jay Shah's company, Cold Axe Research.
Yeah, I caught that too.
The host of the series mentioned it's a family business.
I love that. You're a family business. You think, I don't know, a bakery or a hardware store.
Right. Shah and Sons.
Not a high-end consultancy that specializes in writing custom GPU kernels for massive AI models.
It really underscores how much of a craft this is. It's this incredibly niche, specialized skill.
And you see the results. The performance jump from all these human-led optimizations is just staggering.
So let's look at the numbers. They started at, what, 35% utilization on the H100 with Flash Attention 2?
Right. With Flash Attention 3, with the TMA and warp specialization, they jumped from around 350 teraflops to about 750 teraflops.
That's more than double the raw throughput.
And in terms of utilization, they're now hitting up to 85% of the hardware's theoretical maximum.
And for anyone listening who doesn't benchmark chips for a living, getting to 85% of theoretical max it's almost unheard of. Theoretical usually means in a perfect world that doesn't exist.
Exactly. It means there's almost zero waste in your pipeline. Every single transistor is working as hard as it possibly can.
There is one more optimization I want to cover because it really affects how these models feel to us. It's about inference and a trick called GQA packing.
Right. Everything we've talked about is mostly for training or processing a big prompt. But when you're generating text token by token, the work is different. Your query matrix is tiny.
But that big WGMMA unit, it still wants to eat in big chunks.
It does. It's designed to process tiles of, say, 128 elements. If you send it a query for a single token, you're wasting almost all of its capacity. It's like firing up an industrial pizza oven just to cook one little bagel bite.
Very inefficient.
So what they realize is that most modern models use grouped query attention, or GQA. And Shaw's insight was to pack those queries together.
So instead of sending them one by one, you just bundle them up from different attention heads.
You fill the oven tray, you stack queries from different heads into the same tile, so that when you send it to the WGMMA unit, it's fully utilized.
And the speed up from that.
He cited a 6 to 7x speed up in that decoding regime compared to Flash Attention 2.
7 times. That's the difference between an AI that feels like it's thinking and one that feels instantaneous. That's a laggy chatbot versus a real-time voice agent.
It's a huge deal. And again, it all comes down to understanding the shape of your hardware and reshaping your data to make it happy.
So if we zoom out, the story is pretty clear. We hit a memory wall, we solved it with tiling, then the hardware changed underneath us with the H100, and we had to solve it all over again with asynchrony and this warp specialization.
It really proves that software isn't static. You can't just write optimal code and be done.
Yeah.
When the physics of the chip changes, your code has to change, or it just becomes obsolete overnight.
And this brings us to a really interesting, kind of provocative thought. We keep hearing that AI is going to write all the code for us soon. But Jay Shaw's experience seems to suggest that at the very cutting edge, the opposite is happening.
I think so. As the hardware gets more and more specialized, we're talking FP4, sparsity engines, weird new accelerators, the gap between code that works and code that runs fast is just getting wider and wider.
So the more advanced the hardware becomes, the more you need these human artisans who can do that register-level Tetris in their heads.
At least for now, yeah. You need people who can look at a spec sheet and see the bottlenecks before anyone even writes a line of code. We need humans who understand the machine better than the machine understands itself.
That's a pretty comforting thought for all the engineers listening to this. We're not obsolete yet.
Not at all. Just stay curious. The code's open source. Go look at it. It's built on CUTS, which handles a lot of the heavy lifting, but the logic is all there.
Absolutely. We've linked to the paper and Jay's full lecture in the show notes. If you want to see what 750 teraflops of performance looks like in C++SR, go check it out. It's really a thing of beauty.
It really is.
Thanks for diving deep with us today. Until next time.